Welcome back, everybody. Today we're going to look at section 4.3 subspaces. Now, a subspace is a subset of a vector space that satisfies two conditions: that for any vectors or elements, uv in the set, u plus v is in the set. Okay, when that is the case, we say the set is closed, the subset is closed under addition. The second condition is that for any vector in the subset and scalar k, okay, v is in the subset. And when that is the case, we say it's closed under scalar multiplication. If the subset is closed both under addition and closed under scalar multiplication, we say the subset is a subspace. Okay. Now, as a note to item number 2, okay, that the consequence to that if v is in the subset, then k times v is in the subset, requires that 0 must also be in the subset, because a scalar, 0 is a scalar, so 0 times a vector is going to be the 0 vector. And so if it's going to be closed under scalar multiplication, it's going to be required that the 0 vector is in the subset. Now notice that is necessary but not sufficient. So just because 0 is in the subset doesn't mean that what you're working with is a subspace. Okay. So those are the two requirements for a subset to be a subspace. Okay, so looking at our first example. Okay, let S be the a set of all 2 by 2 matrices with 0 in the 1, 1 entry. Show that this subset we're calling S prime is a not S prime. That's just my not notation, my handwriting. Sorry. Show that S is a subspace of 2 by 2 matrices. Okay, so what are we working with here? Okay, we have the set of all 2 by 2 matrices. Okay, so a generic element in that set would be A, B, C, D, where A, B, C, and D are all real numbers. Okay, what they're saying is within this space, vector space, okay, there is a group of matrices that look like this: 0, B, C, D, where B, C, and D are all real numbers, any real numbers that they please to be, but the upper left-hand corner must be 0, and this is the subset that we're working with. Okay, this is the set of all 2 by 2 matrices with real coefficients. Okay, now we want to show that the thing in red is a subspace. That means we have to show that it's closed under addition and closed under scalar multiplication. Okay, so how do we show that it's closed under addition? Well, what you do is you take 2 elements that are in the subset. Okay, so we're talking about things that are in red, so I'm going to describe them, or I'm going to color them in red. Okay, so one element might be 0, B, C, D. So that's one element in the set. Here's another element in the set: 0, X, Y, Z. And what you want to do is that you want to show that when you add them together, you get something that is also in the subset. Okay, so what happens when you add these two 2 by 2 matrices together? Well, what do you get in the upper left-hand corner? 0 plus 0 is 0. B plus x is b plus x. C plus y. And d plus c. Is this matrix the result of adding the two above in the subset S? So I'll pose that question. Is this in S? Well, there's two things to check, okay? Is there 0 in the 1, 1 position? The answer is yes. Okay, in the row 1, column 1, there is a 0. Are there real entries everywhere else? The answer is yes, because b plus x is real because b and x are real. C plus y is real because c and y are both real. D plus z is real because d and z are both real. So their sums are real. So perfect. We're closed under addition. Okay, what about scalar multiplication? Okay, so you're going to take an element. So we'll go back to 0, b, c, and d. And we're going to multiply it by some scalar we'll call k. So what does that give us? Okay, that gives us 0 times k, that's 0. That gives us bk, ck, and dk. Okay, is this right here, the result of a scalar multiple, a matrix that's in our set? So question is there a 0 in the 1, 1 position? The answer is yes. Are there real entries everywhere else? Okay, well, B is real, K is real, so BK is real, CK is real, and DK is real. So we're closed under scalar multiplication. We're closed under addition. So therefore, S, a subset of M2R, 2 by 2R, is a subspace. There you go. Now, there's going to be some important implications for what is and isn't a subspace moving forward, okay? But we will get to that as we move forward. Second example. Let S be the set of all vectors in R4 with a 0 in the second entry and a 5 in the fourth. Okay, so what does a generic element look like in R4? Oops, we're going to draw our picture here. Generic element in R4 looks like A, B, C, D. But the subset are the things in R4 that look like what? So this is S. What are the things in R4 look like? A 0 in the second entry and a 5 in the fourth. Well, it doesn't give any restrictions on the first and third, so we can call this A and we can call this C. So the set of all vectors that look like real number 0, real number 5. And you ask yourself, is it closed under addition? Is it closed under scalar multiplication? Scalar multiplication. Okay. We're going to look at scalar multiplication. Okay. So, you take the generic element A0, C5, and you multiply it by some scalar k. What do you get out of this? Okay, you get this to be AK, which is a real number, k times 0, which is a real number, which is 0, which is what it should be, 0k, or CK, which is, sorry, my phone was ringing, CK, which is a real number, and 5k. Now, this is good. Okay, this entry is a real number, that's what it should be. 0 is good because the second slot has to be 0. CK is good because the third entry has to be a real number. 5k is not, because this fourth element must be equal to 5, and that only happens when k is 1. But we can't restrict k to be 1. K's got to be any scalar. So therefore, this is not closed under scalar multiplication. If it's not closed under scalar multiplication, then it's not a subspace. It doesn't matter. We don't need to check and see if it's closed under addition or not, because it's not closed under scalar multiplication, therefore it's not a subspace. All right. So what were to happen if we had started closed under addition first and not under scalar multiplication? Okay. We would look at something that looked like A0, C5, and what? W0, Y5, and we'd be adding these things together. What do you get when you add A and W together? I get A plus W. That's a real number. That's fine. 0 plus 0. That's fine. C plus Y. That's fine. That's a real number. 5 plus 5 is 10. But this fourth element is not 0 or 5, which it needs to be a member of the subset S. So therefore, we have something that is not closed under addition either. Now remember from the front page, there was one thing that was, where did it go? It's right here. A consequence to number 2 is that 0 must be in the subset. It's necessary for it to be the subset to be a subspace, but not sufficient. Okay, in this case, you can see that the element 0, 0, 0, 0 does not live in S. It lives somewhere outside of S because the last element in the entry in the vector must be a 5. Very good. So hopefully you're following along with this. We have a couple more examples that are a little less straightforward, but certainly doable. If I can find my notes. There we go. is the set. So now I'm not saying whether it is or it isn't. I'm telling you, I'm asking the question, is this set of vectors x1, 0, such that x1 is greater than or equal to 0, a subspace? Okay, so now we need to answer that question. Again, what's our generic element in the vector space look like? It looks like x1, x2, where x1 and x2 are real numbers. Our subset, okay, this thing that we're calling S, is the set of all vectors x1, 0, where x1 is greater than or equal to 0. So it's not just any real number, it's a real number that's greater than or equal to 0. Now, first thing to check is 0 is in the subset because x1 can be equal to 0, and if x1 is equal to 0, then 0, 0 is in the subset. Okay, but that doesn't mean it's a subspace. Okay, so first thing I want to do is I want to look at closed under scalar multiplication. Okay, let's take a look at that. If it's closed under scalar multiplication, we would be able to multiply any element in the set by a scalar k and land in the set. So x1, 0. What does that equal? That is equal to k x1 and 0. Is this in S? Okay, so two things to check. Is k times x1 greater than or equal to 0? Is there a 0 in position row 2, column 1? The answer is clear to the second question. There is a 0 in the second slot, so it satisfies that portion of the criteria. But is k x1 greater than or equal to 0? Well, x1 is greater than or equal to 0, and so that means I can multiply x1 by any scalar k and have that be greater than or equal to 0? The answer is no. Okay, that's false. Because if k is a negative number, and I multiply it by x1, which is a positive number, I get something that is less than 0. So therefore, it's not closed under scalar multiplication, therefore is not a subspace. So let's look at number 2. The set of vectors x1, x2 such the product of the two entries is greater than or equal to 0. Okay, so same setup here. Your vector space looks like the set of vectors x1, x2 that are real numbers. The subset is a little different. They're real numbers, x1, x2, such that x1 times x2 is greater than or equal to 0. Okay, that one, I believe, should work well under scalar multiplication. Because if I take k and multiply it by x1, x2, I get kx1 times kx2. And the only thing that I have to verify is kx1 times kx2 greater than or equal to 0, question mark. Okay, well that is equal to k squared times x1, x2. x1, x2 is by definition greater than or equal to 0 because it's in the subset S. K squared is greater than or equal to 0. And I have a product of two things that are greater than or equal to 0, so their product is greater than or equal to 0, and so this works. So we're closed under scalar multiplication, but what about closed under addition? Okay, this one will be a little bit difficult, more difficult to demonstrate. So you can start by looking at two generic elements. Okay, let's let this be x1, x2. Let's make this y1, y2, where x1, x2 is greater than or equal to 0, y1, y2 is greater than or equal to 0. We're going to add those two things together. We will get x1 plus y1, and we will get x2 plus y2. And the question that we're answering, or we need to answer, I'll write it in red, is x1 plus y1 times x2 plus y2 guaranteed to be greater than or equal to 0. Now we can do some multiplication here. This is k1 x2 plus x1 x2 plus x1 y2 plus y1 x2 plus y1 y2. And you want to answer, is that greater than or equal to 0? And this is kind of where it gets complicated. We know that this is greater than or equal to 0. We know that this is greater than or equal to 0. Okay? So the only way for this not to be greater than or equal to 0 is if something happens here that makes that negative. So this is where I start getting skeptical of whether or not the set is closed under addition. Now, clearly, if x1, x2, y1, and y2 are all positive values, this is a true statement. So really, the question that we have to answer is, does this fail when we introduce negatives? Okay, so for example, this has to hold true for any combination of vectors in our subset. And 1 is clearly in our subset. Okay, these are both real elements, and the product of 1 and 1 is 1, which is greater than or equal to 0. So this vector is clearly in our subset. Okay, but so is this vector. Well, hold on. I may have shot too little. Make this a 10. Okay, so is this vector, -2, -2. 1 times 10 is 10. That's in our subset. -2 and -2. The product of this two is 4. That's in our subset as well. If this subset were closed under addition, then when I added them together, I would get something that was in the subset. So what's 1 plus -2? That's -1. What's 10 plus -2? That is 8. So this is in S. This is in S. But this is not in S. Because -1 times 8 is less than 0. So therefore, though we are closed under multiplication, we are not closed under addition. And this fourth example is not a subspace. All right. Not a subspace, not a subspace. Is a subspace, or is S a subspace of R3? Explain. So I actually don't know the answer to that. We have to come up with it. All right. So what do you think? The set of all x, y, z's such that x plus 2y minus 3z is equal to 0. Sorry, my phone's going off again. All right. That should work. So XYZ subset S is the set of all XYZ. So it's the same thing, but there's a condition that x plus 2y minus 3z has to be equal to 0. Now clearly 0 is in this subset, because if x is 0 and y is 0 and z is 0, then this 0 plus 2 times 0 minus 3, 0 is 0. This 0 is in that subset. Okay, so let's look at seeing if it's closed under addition. Let's look at x1, x2, x3, and let's add to it y1, y2, and y3. Now, to be in S, x1 plus x2 plus, x1 plus 2x2 minus 3x3 is equal to 0. And y1 plus 2y2 minus 3y3 is equal to 0. So we know that is true about x1, x2, and x3, y1, y2, and y3. Let's add these things together. What do we get? x1 plus y1, x2 plus y2, x3 plus y3. So the question that we need to answer, and I'll write this in red, is x1 plus y1 plus 2 times x2 plus y2 minus 3 times x3 plus y3 equal to 0. We don't know the answer to that, but that's the thing that we want to know. So let's split apart the left-hand side, okay? So everything that's x's is going to be grouped together, and everything that's y's are going to be grouped together. So I get x1 plus 2x2 when I distribute the 2 through here, minus 3x3 when I distribute the minus 3 through there, plus y1 plus 2y2 minus 3y3. Is that equal to 0? Okay, so all I did is rearrange the terms. I distributed the 2 and the negative 3 and rearranged the terms. If you look at this thing right here, we are told that this is equal to 0 because x1, x2, x3 is an element of our subset. This right here is also equal to 0 because y1, y2, y3 is a vector in our subset. And 0 plus 0 is equal to 0. So we are closed under plus. All right, half the battle is done. Now let's look at scalar multiplication. So I take x1, x2, x3, where x1 plus 2x2 minus 3x3 is equal to 0. And I multiply it by some scalar k. What do I get? I get kx1, kx2, and kx3. The question is, again, I'll write it in red, is kx1 plus 2 times kx2. So the first element plus twice the second element minus 3 times the third equal to 0, question mark. Get this out of here. All right. Kx1 plus 2kx2 minus 3kx3, is that equal to 0? I can pull out a k. I get x1 plus 2x2 minus 3x3. Is that equal to 0? Well, we know that x1, x2, x3 is a vector in S. So we know that this combination of x1, 2x2, and minus 3x3 is equal to 0. So k times something equal to 0 is 0 all the time. And this is true for any k, which is important. Not just true for some, it's true for any k. Therefore, we are closed under scalar multiplication. Therefore, this is a subspace. All right. So that's a good start to section 4.3. Okay, there's a whole other half of this video that will have to come next time. Take care and have a great day.